Sup y'all, D-Snides here. This video is actually a combination of my 3 individual videos, so it is more lengthy, but it gets more to the point. So enjoy.
I strongly advise that you watch an entire section of the video without pausing or stopping, then go back before you take your notes. This will help you hear the whole story or understand the big picture much better as opposed to starting and stopping repeatedly. Look at the image that you have in front of you right here on your screen, and you might ask yourself this basic question: what's wrong with this map? At first glance, it looks like a lot. It looks as if basically the world is completely turned upside down. But if you take a closer look, and we see this image down here, which we call in the geography world a compass rose, which will show you north, south, east, and west. You notice that north is pointing down, so in reality, there's nothing wrong with this map. It is an upside down world map, just to give you an idea about how we are going to open up your eyes to a whole new world you've never seen before. The first section we're going to look at is under map analysis. In this case, I will introduce to you the very fine acronym Total SIG. You need to know it, and you need to love it. Okay, the love part might be a little bit strong, but let's get into it. T is for title. You can see very easy, Chicago and its interconnections. Very simple. Next thing you need to look at is O for orientation. Since you do not see it here, I'm putting in the compass rose. That shows you where north is pointing. So north, south, east, and west. Very important. Okay, going on to D. D is for the date. If this was going to be a historical investigation, you need to look at something in the past. Since we're looking at something more modern, 2008 meets the mold. A stands for author. In the look of any map, you need to try to determine, is this from a reliable source? In this case, the author is from your textbook, so it does fit very nicely. L is for legend. As you can see, the legend is right here in this box. The focus on this is to show you the centrality of Chicago, to show you the importance of Chicago. That's why it's done at the level that it is. Just like the old saying, with all roads leading to Rome, you take a look here and you can see major highways, major railroads, all leading into Chicago, showing it great centrality. Going on to S for scale. This is also important as well. You can see right here at the bottom of the legend, and you've got your scale right here between 0 and 25 kilometers or 0 and 25 miles. It also shows you a good scale because you have 4 different states: Wisconsin, Illinois, Indiana, Michigan, giving you the idea of the importance that Chicago has. Index. Not all maps will have an index, but with all these different cities, if you were going to find Chicago, very easy. But if you want to find, let's say, DeKalb or Plymouth, it'd be difficult to do without an index. In this case as well, you can see a grid has been included also. In this scale, you can see it's actually the lines of latitude and longitude. You see for latitude, you have 43 degrees, 42 degrees, 41. For longitude, you go from 90 to 89 and down. And here you can just see where this is connecting you with those direct coordinates. So, total SIG. Okay, in All About Maps Part 2, we're going to finish looking at map analysis and then get into map projections. Now for a quick word on scale. There are 2 definitions that are basically almost contradictory, so let me explain. When you think of scale, what you tend to think of is the territorial extent of something. You're starting with, let's say, a local scale to a regional scale. You start with something smaller and get larger. This is how most people interpret what scale means. So you get to the national level, or you get to global, and you get the idea that it gets larger and larger, the territorial extent. But in a map, scale means the distance on a map compared to the distance on the Earth. How much of the Earth has been shrunken down to fit on an image. If you don't notice this, that's Pinecrest. So to understand scale in a map sense, it's really representative of a fraction. So if you look at this map with this scale, and you go down towards this map with this scale, you're actually going from smaller scale to larger scale. And that is because it's a smaller fraction compared to a larger fraction. The best way to remember this is that small scale means small detail. Large scale means large detail. So to recap on scale, if you take a look at this map, the instincts that you would have most likely say, hey, this is large scale. It's dealing with a lot of area. But in reality, it is small scale because of the fraction. So if I go to a level where you're looking at a national scale, North America at night, well, this is getting to larger scale. Or if I zoom in even more, you look at Florida at night, this is an even larger scale. The next section to look at is going to be under map projections. So look at this image. When you take a three-dimensional object, you take a sphere like the Earth, and I want to shrink it down so I have an accurate projection. Basically, to understand, a globe is a map. But if you want to carry 20 or 30 globes around, you realize how inefficient that is. So we have to flatten them onto a two-dimensional object, onto a piece of paper or a map. And in this case, you will always have some degree of distortion. You can't avoid it. So you go from 3 dimensions to 2, you will have distortion. Now, this animated image shows how a 3-dimensional sphere is flattened out into 2 dimensions. This is a Dymaxion projection. Its purpose will be explained in just a little while, but I wanted to give you an idea about how at least one projection is created. Now, there are 4 basic classes of map projections. They're based on how they have been derived. So you have conic, cylindrical, planar, oval. But more importantly, I want to talk about how the accuracy of these map projections are done. There are 2 basic types of projections. The first type is conformal. These projections are designed to preserve the shape of the polygons. Now let me explain what a polygon actually is. Polygons are created by the intersection of latitude and longitude. Latitude specifies the north-south position of a point on the Earth. Lines of constant latitude, or called parallels, will run east-west as circles that are parallel to the equator. So if you look at this line here, it represents 0 degrees latitude, that's the equator. Very simply put, you can remember them as rungs of a ladder. So latitude, ladder, you go up or down measuring north or south. Now longitude, on the other hand, that specifies east and west. Longitude is an angular measurement running from the North Pole to the South Pole. The prime meridian passes through the Royal Observatory in Greenwich, England. So you see 0 degrees right here at the prime meridian. So where they intersect, those are the polygons. And in this case, you can see in this particular projection, they are set at right angles, which makes it very good for navigating, but it really does a massive distortion, especially as you get to the poles. Now, the second type of a projection is the equal area projection, which is focused on area preservation. In this instance, you can see that the polygons are distorted, but the shapes and the sizes of the landforms are much more accurate. And that's where the purpose of this one is. Now you can see on these different types of projections where the darker shading is, where you have greater distortion. In the case of cylindrical, you can see where they are in this instance, or in planar as well. So let's go over some named projections that you really do need to know for this course. Start with a couple of conformal projections. First one, we saw this one before, the Mercator projection, put together by a cartographer back in the late 1500s. And this is really a navigator's map. So you can see that all the angles are right angles, and the idea is so that way you can plot a course. The problem is, as you get closer to the poles, you see greater and greater distortion. As you get really higher up, it's almost unusable. This is another one. This is called the Peters projection, sometimes referred to as the Gall-Peters projection. In this case, is almost in reverse. So you can see where you have the equator, and you do have distortion here as well into the poles, but here as well. This actually was a goal also to keep equal area. So it's not just a conformal projection, it's also sometimes considered an equal area projection. So let's look at some more of those as well. This is called an azimuthal projection. It's a planar projection, as you can see how that is. But you need to know these words. This is a Mollweide projection. And again, you can see where the idea is to maintain the equal area, not so much worrying about the angular preservation of the polygons. You can see this one. This is a conic projection, as we had seen before. Okay, I showed you this one before. This is the Fuller, or also known as the Dymaxion projection. Basically what you do is you take a sphere, you turn it into an icosahedron, which is 20 sides, You flatten it out, and here you go. And of course, the goal here is to keep the shapes of the landforms as accurate as humanly possible. And then we look at some of these hybrid projections. This one's very commonly used. It's the Robinson projection. So you're making sort of a compromise between angular preservation and area preservation. This one is a goods interrupted Homolycine map. And as you can see, it's basically that you have peeled an apple. They take the skin off of an apple and you flatten it out, and this is what you tend to see. So the area of the landforms is preserved by cutting into areas of where you would have the water, where you have fewer people. And you can see where distortion is greater. Now we're going to look at modern mapping and some of the technologies that are associated with our world today. Starting off with a very simple term, absolute location. The definition is that absolute location measures exact location and distance. Now, another term that we use to understand absolute location is site. So if we're talking about the site, you're talking about a point or an area on the Earth's surface. So really they are basically synonymous. Now, in today's technology, we have the advantage of the GPS, the Global Positioning System, which really is a satellite navigation system that provides location and time information anywhere on the Earth. It's maintained by the United States, and currently there's around 30 operating satellites, give or take. The diagram to the lower right shows how multiple satellites are used to triangulate your position very accurately. So you can see these satellites that are shown here would be way up in space, not visible by the person, obviously. By using multiple satellites, you can get a very good and accurate point. Now, this animated image, I think I find very interesting. It shows the GPS constellation in motion with the rotating Earth. On average, at least 9 satellites are visible by line of sight at any given point. So you can see the Earth rotating, you can see the satellites in orbit. Because you have at least 9 at any given time, sometimes more, sometimes less, but it ensures good redundancy in case any of the satellites fail or if something is obstructed one way or the other. The other type of location you need to know is relative location, which basically is the location of a place relative to other human and physical features. Synonymous with the other term situation. So we talked about site with absolute location, now we talk about situation with relative location. Again, looking at the map that we've seen before in Chicago, you can see all the connections, all the railroads, all the highways leading into Chicago. Also the accessibility that it has with multiple states and multiple areas. One thing to keep in mind, absolute location doesn't change. Relative location may change. That is why throughout history we've seen civilizations come and go, rise and fall. Now, there are 2 types of maps that you need to be aware of. You have your reference map, which you see here to the left, and the purpose behind a reference map is to show locations of places and geographic features. So you can see this one showing you where major cities are. You might have one that shows you where rivers are or where mountain ranges. Basically, the idea is to show you the absolute locations. The other kind of map is a thematic map. A thematic map will tell you a theme, a story about the degree of an attribute, the pattern of its distribution, or its movement. So we're looking at relative locations here. In this map, talking about the Washington, D.C. metro area, is the median household income by census tract. So it's telling you the relative wealth that you can see. You can see clearly in this map where you see it in green, where you have poorer neighborhoods or lower income areas, and then you can go to see where it gets darker to the red, where you can see the higher income areas. Again, the idea is to give you a theme, tell you a story. Now let's take a look at GIS, Geographic Information Systems. Because of modern computer hardware and software, we're able to store and analyze layers of spatial data. Now this is also very important, by the way. Notice I pronounced it spatial. I don't want to hear anybody pronouncing it as spatial. That drives me nuts. There's no such thing as anything spatial, it is spatial, dealing with space, an area. Look at the image to the right, and that shows you land cover. So I will show you vegetation, show you trees, and you can see all that. Now, what if I wanted to focus on where rivers were located? Rivers, streams, any kind of body of water. I can see some major ones along these areas, but to see the smaller tributaries, much more difficult. So go to another layer of data, and here you go. So by layering the data, you get to see less noise, less mess. So I go from this to this. Now let's take a look at where the roads are. So if you want to see that as a different layer altogether. Now the power of GIS isn't just to break down between one slide or another, but to actually superimpose one on top of the other. So I can do this. So I can put it into where the rivers are, and you can see a better story of actually why things are where they are. So you look at this area where you see there's very few roads. The good explanation for that, of course, is that that's a major body of water. Or where you see other ones, you can zoom that in there. Now, I put in the land cover behind this. Unfortunately, the image is not very good, but you get the idea that if you were to put layer on top of layer on top of layer, it tells you a more telling story than just giving you one little piece of information. You add more and more information. So roads and rivers and land cover. Now, last term we're going to use here is talking about remote sensing. If you go back to ancient world, you can only see as far as your eyes can see. Now we talk about remote sensing, a method of collecting data by instruments that are physically distant from the area of study. So you could use aircraft or radar or satellite image like this one is here. If you haven't figured out what this is showing, this is Katrina. This is 2005, the hurricane that devastated New Orleans, among other places. Now we see a satellite image of New Orleans. If you take a look at this little white dot here, that's the Superdome. Now, one of the areas to focus in on, highlighted for you here, is the French Quarter. Now, the French settlers originally went in this area for a very good reason. If you take a look at elevation, you notice that there's a lot of places that are below sea level. Everything that you see here in the blue, okay, or the light blue. The places that you get to in the red are as high as about, we're talking about 30 feet. So we're not talking about a high elevation, but certainly if there was going to be flooding or some other issue, that would be a big benefit. Now take a look at what happened in 2005 as a result of Hurricane Katrina. So you can see where there was great devastation and flooding that took place because of this, where the levees had broken that were holding back the waters of like Pontchartrain or other areas in New Orleans. You take a look, you can see where there was some minor flooding, all the way down to where there was more and more major flooding, going up to 7 to 8 feet in some areas. If I was to show you another one, I don't have it to show you at this point, but if you were to see income, what do you think you would see? More than likely, the lower income areas, the lower cost land would be in places that were more likely to flood, and the higher cost in other territories, like around where the French Quarter would be in a nicer region. Again, common sense. Now, maps may show you information, may show you data, but nothing quite hits as hard as seeing the real images yourself. So this is the Superdome before Hurricane Katrina in 2005, and this is what it looks like afterward. Well, in black and white anyway. So here it is before, and then with a lot of wind damage, and then a lot of flooding that was around it. Of course, this is the Superdome today, so it's all fixed up. And now a special service announcement from our sponsor, Thor.
People often wonder how I stay so mighty. I've got one word for you. Exercise.